Hello, I'm Sarah Mukhtar, Computation Environmental Designer at Pedestrian Associates, and I'll be presenting to you work on behalf of all the paper authors on using conditional generative adversarial networks for pedestrian wind flow approximation. As architects, we shape the built environment in our cities, and the impact of our work extends beyond just the boundaries of one specific project or one specific intervention. And by designing buildings, we're also creating the spaces in between, creating microclimates around them. And those can be positively or negatively affected by those interventions and can affect the quality of the spaces and when and for what they can be used for. And in contrast to indoor environments, which are typically controlled, and to rural areas, which are largely affected by just meteorological conditions, urban microclimates experience larger variations and complexities in wind flow patterns, surface conditions, sky and solar exposures, and those are influenced by the morphology of the buildings, the density, the materials, the orientation of the buildings, um, parameters that are design decisions early on in the process and which have a substantial role in defining the performance of the spaces. And due to an increased complexity, which requires a multidisciplinary skill set, some of these systems are only quantifiable using high computational power. While some of those are easier to measure or simulate than others, when modeling, for instance, through either computational fluid dynamics or wind tunnel testing, is particularly complex and time-consuming. In order to be able to shape the built environment to promote favorable conditions, having the capacity to measure iteratively the performance of a design iteration is quite key, and not just for the building in question, but as well to the surrounding public realm. So we wanted to tackle that problem of not being able to bring wind microclimate insights in the early design process, which is what drove us to start looking into ways of making this process faster and looking at machine learning to do so. There are a number of research directions that have been explored in the past to address this problem of time-expensive CFD simulations. Some of those were about developing advanced numerical methods, some others about increasing computing capabilities or integrating both. In the context of external urban wind flows, GPU-enabled methods such as fast fluid dynamics or the lattice-Bostock methods were explored, for instance, but while those are underway to be developed to suit the urban scale applications, they have not yet been demonstrated to provide reliable accuracy for pedestrian wind comfort applications. And additionally, they rely on high computing requirements and cannot yet be integrated in an architectural workflow in a way that can support iterative early design explorations. Data-driven approaches as well have been proposed as an alternative to approximate wind flow through learning a relationship between the geometry represented as input feature vectors and their corresponding measured fields. And more recently, deep learning approaches started to be investigated as well. In the last few years, deep learning methods started gaining traction due to their remarkable capacity to learn complex, high-dimensional, and nonlinear dynamic systems. More recently, as well as gained traction in modeling turbulent flows. The great potential of exploring image-based deep learning approaches stems from their ability to learn solely on observation without any knowledge of governing equations, and their agnostic nature to data sources, which means that it's accessible to a wider audience like architects, engineers, and there are no limitations on the software, platform, or simulation method used to generate the dataset, as well as the ability to always augment the training set with more data as it becomes available. And there are implementations of convolutional neural networks, as well as generative adversarial networks, which have the additional ability to learn implicit data distribution without the need to define an explicit loss function. But the limitations of those explorations is for urban wind applications that they're not non-generalizable and they're quite specific to their application, and we cannot directly use them to infer wind flow in complex urban contexts. And the suitability for pedestrian wind comfort applications have not yet been explored. And because this approach has not yet been explored in the outdoor wind flow context, the main contribution of this research is to explore the suitability of using conditional generative adversarial networks and the limitations of this method for this application. But it's also about investigating what are the characteristics of that training set and what encoding strategy would be best, whether it is about encoding the geometry and the boundary conditions or encoding the outputs of the CFD simulations. It's about identifying what simplifications are acceptable for this purpose. In order to achieve that, we developed a workflow that would allow us to apply the conditional GAN model. And the process starts with generating a synthetic data set based on CFD simulations of procedurally generated urban configurations. And then that's followed by preparing the training dataset, which is a major component of that, exploring the different geometry representations and the different encoding techniques. And the parameters that we decided to explore were the image sizes, the training set size, the geometric diversity within each set, and in terms of encoding strategies, the color map representations, and how we represent the geometry in an image. And that's followed by the machine learning training and testing, and finally the model performance and evaluation. So we start the process with generating sets of geometrical configurations to represent the urban conditions. And the guiding principle for that stage was to create a larger design representation potential of the urban context while limiting the number of cases. So we had two sets, one simple geometries of 2 to 3 buildings, and the second one had more complexity and a larger fidelity to the rules governing the urban grids and morphologies of our cities. We set up steady-state ran CFD simulations following industry standards for pedestrian wind flow applications. We used the realizable K-epsilon turbulence model, and we ran that through OpenFOAM through Butterfly. We used the rectangular domain, height range from 40 to 250. We used the cell size of 3 refinement at the pedestrian levels as well as to the geometry. To convert a 3D geometry into a 2D matrix, we created a height map on a Cartesian grid, and the zero level here was defined as the wind speed height of interest. And in areas where the buildings extend beyond that height of interest, a positive distance was assigned, and in other cases, the negative distance was assigned to whether it's a building roof that is below or the ground plane was assigned. And for each simulation case, an automation process was developed to extract the mesh geometries and their corresponding speed values at the heights of interest, which start at 1.5 meters above the ground, up to 36 meters at 1.5 meter intervals. So we explored different color map representations, and here wanted to see whether the color contrast would have an impact on the accuracy and legibility of results, and whether their functional representation or the number of unique colors would have an impact. So here the first two color maps that we chose are high contrast. They don't follow a linear function, and they require a clustering method to be converted back to a value, while the third one has 766 unique colors, but has lower contrast, but a much faster instant feedback from color to value since it's a linear function. We explored as well the impact of the image size on the training and the results. So we extracted 3 image resolutions for each, 256, 512, and 1024 pixel images. And in addition to the implications on training, which we were interested in identifying, the selection of the image size as well puts a threshold to the representation accuracy of the set. So that means that 256 pixel image, one pixel will represent 2 meters, and 0.5 meters for a 1024 pixel image. The last training set parameter we explored combines the training set size and the geometry complexity within each set. So we had one set consisting only of the complex urban configurations, which was a smaller set, and another one which combined both urban configurations and simple geometries together. And just like any other conditional generative adversarial network, it consists of 2 networks, a generator and discriminator, and the generator output is conditioned on a very specific input image rather than a broader distribution of images in the target domain. And the generator is trained on paired images, input and output images, and the network learns to generate a fake output that is visually close to the real one. And at the same time, there is a discriminator, which is trained to detect which output is real and which one is fake. In order to evaluate and compare the different models, we use the mean absolute error and the 90th percentile error to compare between them. And the first thing we looked at was the different color maps, and what we found out was the high contrast, smooth visualizations of the turbo and spectral maps. They outweighed the 3 times larger number of unique colors in the inferno linear color map. And then looking at the color ranges, we found that a shorter color gradient range representation achieves lower errors as well as more visually legible maps. General improvement was as well observed with larger images, and the rise in accuracy, however, comes at a steep computational cost, where by 16 times time difference between a 256 and a 1024 pixels at training. And when we started looking at the geometries and diversity and the impact of that on the results, we found that the geometries deviating from the continuous street grids and consistent building morphologies were generally associated with the highest sources of speed differences. So the paper presented a conditional generative adversarial network approach to developing a surrogate model for the design contribution of urban morphologies to pedestrian wind flow conditions, and it was capable of producing an accuracy of 0.8 to 0.5 meters per second within seconds, a fraction of what would be needed for an equivalent CPU-based CFD simulation. And the selection of data set encoding strategy and training set parameter geometrical diversity was shown to have an impact on the accuracy of the results, and about 0.1 meters per second change for each strategy to an accumulated 0.3 meters per second error difference. The proposed approach presents some challenges and limitations. Firstly, as with other deep learning approaches for physics-important applications, machine learning models are prone to overfitting, and there's no direct methodology to ensure that this can be avoided, and that it will be applicable to all morphologies that are quite far from the training set. It is essential to cross-validate the model against overfitting. And as was observed within the results, although the model was able to infer wind speeds on urban configurations outside the training set, the larger disparity between simulation and model prediction was observed when the continuous street grids and building shapes were disturbed, and this suggests that a larger repertoire of urban morphologies is desirable to improve the accuracy. The second thing is that the encoding strategy presented, it represents, yes, a larger variety of urban morphologies, but it is limited to buildings that are continuously solid and that cannot yet represent elements such as tunnels, bridges, curved terraces, and so on. So other representations of 3D geometries can be further explored to expand the model capabilities through either augmenting the image encoding for voids using additional color layers or exploring adapted mesh or voxel data structures in a different model architecture. And the third limitation is that the creation of synthetic training set is needed because there's a lack of structured data for CFD simulations, and the computation expense of run CFD simulations limit the capacity to expand it considerably. And the process as well requires a lot of automation of the processes for data extraction, validation, and for the quality control. Although outside the scope of this paper, we would like to conclude by showing you how the machine learning model can be used to infer wind speeds directly within an architect's design workflow. And in this sense, this brings insights of performance variability and the impact of that on wind, and insights that cannot be gained from one high accuracy simulation that is done later in the design process. And thank you. I would like to take time to acknowledge our co-authors, Alex and Carlos, as well as thank Jason, Max, Demi, and Theodore for their help during the initial phases of the project.